Is there an easy way to pick up the basics for carbon NMR? What are the things that are really important and what should you not waste too much time on? I'm going to tell you what seems to work for a lot of people. First, you need to understand a bit of physics for NMR. It's not too bad. Second, NMR uses chemical shift delta values all the time. You need to know these so well that you can define them on your own. Third, you need to be able to figure out how many magnetically inequivalent carbons a compound contains. This is not hard, but you need practice to be able to do it. I'm going to show you how to practice. NMR machines operate at the low energy, long wavelength end of the electromagnetic spectrum. If you don't know already, you may be surprised that some nuclei have a nuclear spin. Spins of 13C and 1H can be plus a half or minus a half. But if there's no molecular field, there's no difference between these. They have the same energy. However, in the presence of a magnetic field, let's call it B0, these spins either align or oppose. Strong fields give bigger energy differences. But in any case, however strong the field is, those energy differences are very small. Population differences of nuclei between the aligned and the opposed states are given by Boltzmann distributions. You don't have to remember this equation, but understand the energy difference delta E is very small between the aligned and the opposed states. So the opposed state only has marginally less population than the aligned one. That's why NMR machines have big magnets. This increases the delta E, that increases the population difference, and that increases the absorbance of the signal. The sensitivity of the machine is proportional to that absorbance signal. Nuclei can be flipped between their aligned and opposed states by applying a perpendicular magnetic field. That perpendicular field can be a radio frequency pulse because radio waves generate magnetism as they travel. It's convenient to think about the magnetic field splitting the energy levels, that's B0 as we defined before, in terms of frequencies too, and express them in hertz. Therefore, we measure the magnetic field in terms of frequency. NMR machines tend to range from 400 megahertz to 1 gigahertz. Let's think of chemical shifts that way too. Chemical shift is the resonating frequency minus the resonating frequency of a reference compound, all divided by the resonating frequency of the reference compound. Chemical shifts, delta, have no units. They're just the ratio of two frequencies. Frequency differences for different resonances in the same molecule are small compared to the absolute frequency. So chemical shifts are measured in parts per million, a million, where 1 part per million is a millionth of the absolute frequency. Chemical shift values are proportional to the frequency associated with B0. That's the operating frequency. 1 part per million on a 500 times 10 to the 6 hertz, that's 500 megahertz, NMR machine corresponds to 500 hertz. On a 600 megahertz machine, it is 600 hertz. On a 1 gigahertz NMR machine, it is 1000 hertz. That means differences between resonance measured in hertz are larger for larger spectrometers. Bigger magnets give more dispersion in NMR. For C13 NMR, the chemical shifts where most nuclei resonate is between 0 and about 210 ppm. For protons, it's much less. It's between 0 and 10 ppm. So we say that carbon NMR has a much higher dispersion than proton NMR. It's easier to see the peaks apart. Two terms are very important to remember. The region near the left of the NMR spectrum is called downfield or de-shielded. It means that less energy is required to flip nuclei that resonate in that end of the spectrum because they're less shielded by their molecular environments, by the atoms around them. At the right of the spectrum is the shielded high field region. For atoms that resonate there, it takes relatively more magnetism to flip them because their molecular environment is protecting them from the magnetic field more. No one can remember all possible chemical shifts. I suggest you remember just a few ranges. If you memorize these, you can learn to guess at other chemical shifts in the spectrum. Most downfield are carbonyl COs, and most upfield are aliphatic carbons with no electronegative substituents or alkenes attached to them. Beginning with the aliphatic carbons, attachment of a double bond, a carbonyl group, or an electronegative atom gives a downfield shift. Alkenes, alkynes, and aromatic compounds tend to be the next downfield, in that order approximately. Carbonyls with an electronegative substituent attached, that's O double bond C X, like esters and amides, tend to be a little bit upfield of ones without an X group attached. Please try to remember those ranges if you can. If you can't, refer back to this chart as you practice, and eventually they'll come to mind more easily. But before you do that, let's look at a relatively underappreciated step that will increase chances of success. I call it a secret sauce. That is, learn how to predict the number of magnetically inequivalent carbons in a molecule. Carbons that can be interchanged by an axis of symmetry or by rotation around a line of symmetry are equivalent. Let's consider naphthalene. Well, I count two planes of symmetry perpendicular to the plane that the aromatic rings are in. So then there are three different types of carbons. Agree? Adding a methyl group to naphthalene breaks those planes of symmetry. So now all 11 carbons are inequivalent. They may accidentally have the same chemical shifts or chemical shifts so close that you can't tell them apart, but mostly they won't. Putting a methyl group exactly here increases the symmetry by introducing a point of rotation, even though there are no planes of symmetry other than the one that the naphthalene rests in. That means I count 6 inequivalent carbons for this molecule. Check, because I often make mistakes. Moving the methyl group around one disrupts that axis of rotation, but introduces a plane of symmetry. So now I count 7 inequivalent carbons. Do you agree? Probably you'll find this difficult to do on your own at first. That is why my ebook on spectroscopy, on Apple Books, on Kindle, on Vital Source, has many problems like these for you to practice on. The skill of being able to assign the number of inequivalent carbons is extremely valuable. Imagine you have a compound, you know the structure, but if you don't know how many carbons to expect, you don't know which ones to assign. It's even harder to deduce the structure of a compound from its 13C NMR spectra if we don't understand magnetically inequivalent carbons. To master interpretation of 13C NMR, it's best to practice on lots of spectra. If you don't have them to practice on, I know at least 2 ways to simulate them. This is how you do it in the ChemDraw program, which some universities make available to students, and you can buy. Draw a structure, highlight it. Under the Structure drop-down menu, pick Predict C13 NMR Spectrum. ChemDraw returns a prediction as a list and draws a simulated spectrum. Then you just check the assignments against yours. Let's look at those naphthalenes where I predicted the number of magnetically inequivalent carbons. Let's see if ChemDraw agrees with me. I predicted 3 for naphthalene itself, and I got it right. My reasoning was that there would be 11 different carbons for the methyl substituted system. From ChemDraw's prediction, I couldn't count 11 peaks because some of them were too close together. So I had to only look at the list, and there are indeed 11 different types of carbons listed there. There were 6 for the system with the axis of symmetry, and there were 7 for the one with the plane of symmetry, just as I expected. These compounds only have aromatic carbons at relatively downfield delta values and one methyl group at a high field delta value, so they don't give much opportunity to assign chemical shifts. In any case, it's often not possible to assign aromatic carbons in the aromatic region without some other technique. Let's look at ethyl acetate then, and look at the chemical shift assignments there. All 4 carbons in this molecule are inequivalent, so we would expect 4 C13 NMR resonances. When assigning, pick peaks at extreme values first. For ethyl acetate, there should be a carbonyl around about 200, and there is. It's a little below 200 because it's of the O double bond CX type. There should be a methyl group of the ethyl at very high field, and there is. The methyl group attached to the carbonyl is a little bit downfield of this, and the CH2 attached to the oxygen is more downfield. The assignment by ChemDraw and me agree. For 3-pentanone, I expect 3 inequivalent carbons. At about 200 ppm, there's a carbonyl. In the high field region, there's 2 equivalent methyl groups, coincident. And next to that is a signal for the CH2, which is shifted a bit downfield because it's adjacent to the carbonyl group. In fact, both CH2s are equivalent. A word of warning. I simulated the spectrum of naphthalene by asking ChatGPT to do this. Simulate the 13C NMR spectrum of naphthalene and output the result as an SVG file. It predicted 4 peaks, which is wrong. Also, when I click on the link for downloading, I get an error. I don't know why this is. If anyone does, please let me know in the comments below. In summary, this video has covered what I think is the best approach to mastering the fundamentals of 13C NMR. I hope you have the energy to follow them, and I hope you find them useful. Thanks to Eric and Marshall at the Engine Room in Southport, UK, for letting me use their studio. Thank you too for watching. Bye-bye.